Well, let's begin from where we ended the previous class. We now know that a light amplifier can be pictured in the, we have an inverted medium, that is a medium in which population has been inverted between two energy levels. That means the excited state has now more population than the ground state. So such a medium is also called active medium. Now we shine this medium by a beam of light that comprises of identical resonating photons. Identical photons means these are all coherent. And resonating photon means the photon's energy, which is h nu, the frequency is nu, matches exactly the energy difference between these two energy states. Therefore, now we know that as these resonating photons travels through the inverted population inverted medium, they will interact more often with the excited atoms than they would interact with the atoms in the ground state, simply because the number of excited atoms is more than that of the, because it is a population inverted medium. And interaction with the stimulated, so excited state atoms will cause stimulation, and as a result, these atoms will come down to the ground state and will add another identical photons to this incident group of photons. And because there will be more stimulated emission than absorption, so the medium would eventually give out amplified coherent light. Now, so this is now a light amplifier, which amplifies light. And you will appreciate that higher is the population inversion, more would be the amplification. If you take more population in the excited state from the ground state, the rate of stimulated emission will be even more, so it will amplify light at a faster rate. Therefore, the amplification will be more. In other words, we can say that, so higher is the population inversion, more would be amplified. In other words, we can say that the gain of this optical amplifier increases with increasing population inversion. Now you see, a laser is an acronym for light amplification by stimulated emission of radiation. Therefore, a laser also amplifies light, but surely it does not require an input coherent source of light for its operation. If it did, then the laser would have lost almost all its charm. So how does it work then? It amplifies light, yet it does not require an input source for amplification. Well, to understand this, we must know what is a cavity. For this, we once again delve into a fluorescent tube light and pose this question: can a tube light perform as a laser even if population inversion exists? We have, of course, earlier seen that without population inversion, amplification is not possible. Amplification of light is not possible because there will be more absorption than stimulation. Now we say that there is population inversion, and we ask if, in that case, the tube light can perform. We now know that discharge in the in this fluorescent tube manifests through creation of a fraction of positively charged ion, positive ion, from this neutral atom, and another fraction of this neutral atom is driven into excited state. Of course, there will be electrons present in equal number as that of positive ions for obvious reasons. And now we begin with the presumption that a population inversion exists in this discharge tube. That means the excited state, this is the ground state where we have neutral species. In the excited state, we have the neutral atoms in the excited state. And we assume that population inversion exists. That means the number of atoms in the excited states exceeds that in the ground state. Now, as these excited atoms begin dropping down to the ground state, they will emit photons spontaneously all around. Basically, the photon will travel in 4 pi solid. In 2 dimension, I show that as the excited atoms come down, they're emitting photon. Now we catch one such photon at the left end of this tube that travels along the axis towards the right end. Now, as there is population inversion, therefore, this photon, as it travels, number of it would be multiplied by the time it reaches the other end. The obvious question is, by how much? By how much its number has multiplied? Well, as you know, light travels at lightning speed, 3 into 10 to the power meter per second, to be precise. And these atoms, gaseous atoms, occupy only a tiny fraction of the total volume of this discharge tube. And they move in zigzag fashion, as we already know from kinetic theory of gases. Therefore, most of the spaces in this volume is actually empty. Therefore, in the split second that light takes to reach, to traverse the typical length of a tube light, there will be very, very few interactions, photon to atom interaction, and hence the growth. But there will be amplification, of course, because there is population inversion, but light cannot grow and develop into a beam where it can produce an effect which will be visible by the naked eye. In the split second that the light takes to traverse the typical length of a tube light, the photons traveling in either direction will grow in numbers, but cannot develop into a beam of light to produce an effect that is visible to the naked eye. It would be true for photons which are traveling from left to right, or photons which are traveling from right to left, and even for photons which begin their journey at progressively much closer distance from the ends. Therefore, we are now in a position to answer this question that we posed. Although the presence of population inversion ensures that there will be amplification of those initial spontaneously emitted photons either direction, but it cannot develop into a beam of light typical of lasers. So, what will be the remedy? Remedy, of course, would be to increase the number of photon-atom interactions. How do you do that? Obviously, one option would be stack up the atoms more closely. So that would essentially increase the pressure of the gas so that their more closely spaced compared to the previous case where they were more scarcely spaced, more spaced more widely. However, this will work only up to a certain extent, as electrons now will have less path for acceleration. That is because if you are bringing the atoms closer, they will collide more frequently with the electron. So the electron will have less path for acceleration, and the electron needs to accelerate to acquire kinetic energy because it must have enough energy to cause further ionization, sustain the discharge. Also, the kinetic energy is required for excitation because we know that the electron with some appropriate kinetic energy, when collides with an atom, it can result in ionization of the atom, where an additional electron is created, and also electron sometimes can collide with these neutral atoms in an inelastic manner, so that part of the kinetic energy is transferred to the atom with its internal energy, and electron moves with less kinetic. But if electron cannot acquire enough kinetic energy, so there is difficulty in achieving both sustaining the discharge and also attaining population inversion. So then this is not going to. The second, of course, would be to increase the length of interaction. That means you increase the length of the discharge where you have population medium. But it's quite impractical, as you would appreciate, that the length of the tube can be, say, from a meter, it can be increased to just several meters, but surely not kilometers. Therefore, this is also going to be an impractical solution. What will be the best option? The best option will be to make the photons traverse the population inverted medium multiple times, time and again. You have the population inverted medium. You want that light should travel in this medium multiple times, time and again. That will increase the length of interaction, increase the photon interactions in turn. So how do you do that? Well, if you put, say, a 100% reflective mirror, plane mirror, on one end, then the light that shines onto it will be reflected and it will travel back. So this will allow doubling the interaction length. If you put another mirror exactly parallel to the earlier, that should solve the problem because it would allow light to move to and fro almost endlessly. And because it is a population medium, as the light, that means resonant photons, will travel back and forth, they will stimulate the excited atom, and by virtue of stimulated emission, their number will grow. So in such a system, which we can call cavity, in a very crude sense, you can multiply the number of photons exponentially, and there is a possibility that you can actually develop this light into a beam of light. However, there are still some issues which have to be addressed. First is, there is no tolerance on the degree of parallelism. Because you see, if Let us assume that this mirror is perpendicular to the axis tube, while this mirror slightly. But it is can be easily shown that if you suppose begin from the center of this, from this axis of this cavity, then the ray of light after and the axial ray of light as it travels to and fro between the reflectors gradually shifts laterally before eventually flying away. So if you use two plane mirrors and try to form this cavity, it will be very critical to the alignment. It will not accept even slight misalignment. The beam will just, light will just walk off after few to and fro journeys to fly away. Because plane cavity does not allow any tolerance on error. Adding concavity to one of the beams, so this will add stability to the cavity because the concave mirror focuses a beam of light and it will offset the critical dependence on the degree of tolerance. So then, for the scheme to operate, we must have two mirrors. One could be plane, the other is concave, and there both the mirrors are perpendicular to the axis, so they are parallel to each other. However, there is still another issue. If both the mirrors 100% reflective, this of course is slightly. This of course is second mirror is concave. But if both are 100% reflective, then of course light is growing inside the cavity because of amplification due to stimulated emission of radiation. But there must be a way to couple part of this light inside, from inside the cavity out, which will of course form the laser output, the beam of light. For that to happen, one of the cavity mirror needs to be partially transmitted. That means it will reflect part of the light and transmit the rest, which will be useful loss from the cavity. The cavity is losing light, but this useful loss will form the laser. But we will see due course that you cannot have any arbitrary value of the transmission, percentile transmission of this wave. What I mean is that by that, suppose 100 photons falls on it, and if it reflects 80 of them, transmits 20, then 20% is the transmission of the cavity. What I want to say that we will see in future, some of the later lecture, that you cannot have any value of this transmission. It cannot exceed certain maximum value, which is called the threshold value. Well, we will come to that maybe in the next lecture. But now let us take a deeper look in the cavity. So let us consider a typical cavity where suppose both the mirrors have 99% reflectivity and they are placed parallel to each other at a given separation. And let us assume that we shine this cavity by a beam of light of power 1. Now, the front mirror is 99%. So the cavity will reflect 1%, will reflect 99% of this 1 watt. 1 watt means 1000 milliwatt. So 990 milliwatt will be reflected by the cavity. And only 1%, that is remaining 10 milliwatt, will be transmitted inside. Now of this 10 milliwatt, which shines on the rear mirror, it is going to reflect again 99% back. So 10 milliwatt with 99% is reflected. Only 1% of 10 milliwatt will be transmitted. 1% of 10 milliwatt. It is, I think, 100 microwatt power that will be transmitted by the from this incident 1 watt power. So essentially, cavity hardly transmits anything of the incident light. If this were true, the cavity would have lost almost all its importance in the context of a laser. Well, a very simple experiment will make the cavity reveal its deepest secret. For this experiment, we derive this light beam of 1 watt from a tunable source. A tunable source is one that gives out light of continuously tunable wavelength. Tunable wavelength. That means the output of the laser's wavelength can be changed continuously across a certain region of the spectrum. And in order to monitor the transmission of the cavity, because we just saw that the cavity would hardly transmit it, so we want to probe it more in a more deeper manner. So you want to monitor the transmission of this cavity as a function of the wavelength of this, because this light is not tunable, so you can change its wavelength. So in order to monitor its transmission as a function of wavelength, we place a detector on other side of the cavity and measure the intensity of the transmitted light. The result of this experiment is recorded. It would be seen that for most of the wavelengths, that is this, the cavity hardly transmits anything. This is the intensity transmitted by the cavity, and this is the wavelength. For most of the wavelength, as you can see, the cavity hardly transmits 0 watt. 0 watt. Quite understandable. That's what we just calculated. However, what is intriguing is that at certain discrete wavelength, the cavity transmits almost whatever is incident on it, the entire 1 watt. For these wavelengths, the cavity is said to be on resonance. So then what we found? We found that true, for most of the wavelengths, cavity hardly transmits anything, almost 0. That's what we calculated. From 1 watt, if you just calculate based on the reflectivity of the front and the back mirrors, then it would have transmitted just 100 microwatt. So for most of the wavelengths, certain discrete wavelengths, the cavity transmits everything that shines. It for those wavelengths, for which the cavity transmits whatever shines onto it, the entire 100%. It is said to be on resonance, because those wavelengths are resonant to this cavity. And a non-resonant cavity is one that reflects whatever is incident on it, almost the entire 100%. Of course, very little comes out, but that is almost negligible. So there, the cavity is non-resonant. Thus, we see that a resonant cavity transmits whatever shines onto it. A non-resonant cavity reflects everything that is incident. On closer examination, it would be seen that those wavelengths, half of which times an integer fits exactly inside the cavity, are actually resonant to the cavity. So the resonant equation can be written as n into lambda by 2 equal to L, where L is the length of the cavity, n is an integer, and lambda is the wavelength. Illustration of two examples of resonance occurring in a cavity for two different wavelengths are shown here. For the longer wavelength, you will see that the resonance condition is satisfied for an integer value of 8, while for the shorter wavelength, the resonance condition is satisfied for an integer value of 16. In reality, however, the value of n will be much higher. You can calculate for visible light, you plug in values in this for a visible light, which could be, say, blue light, 500 nanometer wavelength, and for a cavity of length 1 meter, you will see that n can run into several millions. However, you may be still wondering, so what? Even if there is a, all right, this equation, resonant equation that we just wrote, n into lambda by 2 equal to L, in terms of frequency, it can be represented as n into c by 2 nu equal to L. Nu we can actually call n, mu n, that is the frequency corresponding to the integer value n. So nu n will be equal to nc by 2L. These discrete frequencies, nu 1, nu 2, nu 3, nu 4, so on, they are called cavity modes, which can oscillate back and forth inside the cavity without decay. And the spacing between two adjacent cavity modes is called free spectral range of the cavity, and it can be easily shown to be nu n plus 1 minus nu n equal to, if we put the value of n as n plus 1 in this, so n plus 1 into c by 2l minus nc by 2l, which is equal to c by 2. That means the free spectral range of the cavity is inversely proportional to the length of the cavity. So for a long cavity, the cavity modes would be more closely spaced. For a short cavity, the cavity mode would be more widely spaced. But you may be still wondering, so what? Even if there is a resonance, the front cavity, which is 99% reflective, will still reflect 99% of whatever is incident on it. How come, therefore, everything goes to the other side in the first place? Well, this can be understood by referring to this slide. You see, in the beginning, the intracavity photon flux, that is the density of photon present inside the cavity, is 0. Now we shine this cavity by a beam of light of the power 1 watt, continuous beam, and it is resonant to the cavity. That means the light can oscillate back and forth without decaying. Now, as the input light is continuous, therefore the tiny fraction of light that gets trickled inside this will continue to grow inside because it oscillates back and forth. And therefore the intracavity power will continue to rise and rise until and unless an equilibrium condition is reached, which in this particular case occurs at a power level of 100 watt. 100 watt. You see, 1% of 100 watt is 1 watt. So in equilibrium, the cavity gives out 1 watt as its output, and the same 1 watt is also incident on the cavity as its input. Thus, you see, a resonant cavity transmits whatever light is incident on it. If it were not, wavelength was not resonant to it, then it won't be able to oscillate back and forth, and the intracavity flux will not build up, and the cavity will give out the tiny negligible that which is flux. I just want to mention here that this resonance is the analogous to the Bohr's orbits of electron. You know, electron can oscillate only in those orbits without decaying, into which its de-Broglie wavelength fits an integer number of times. All right. So now, next class we will see how this resonance condition of a cavity can be translated to build a laser.